Okie dokie, day 6, part 3. As you can see, I've done a little bit of offline work. I did actually record a lot of the offline work, but I got a bit stumped. And I didn't think you needed to see me just sort of sitting there thinking. And had I not just deleted the file, I could have spliced these two videos together. This will be nice and short. I'm not going to continue actual part 2 of the day in this video, because I do need to go and do some holiday planning. But I'm going to go over what the issue was. So there were two issues. The first issue is that nodes could be out of order. So, and they could be completely out of order, random, multiple breaks, lots of gaps in between them. So in my short example, we could have encountered node D before there is a child called node D. So we get here and we say, well, we are looking for, we are looking for, in our main tree, our head, we are looking for a child with ID of D, and we don't find it. So we say, okay, that's fine. Let's look through our orphan nodes. Yeah, let's look through our orphan nodes, and if we have an orphan node with ID of D, this works. Got the answer right. Now I need to explain how it works. Right. Step 1. Create a node of D which has C which has no children. Get to D. Get to node E, which has a parent of D. Okay. Now we've created the child with an ID of E, and now we're looking for the node D to put this child inside. So if it doesn't exist in the main tree, we are going to look through all our orphan nodes for something with an ID of D, and if we find it, we're going to insert child E into D. In the recording I deleted, there were lots of B's going into D's, or B's that wanted D's. I thought I should probably keep that bad phrasing. I mean, it might naturally come up later. The joke being dicks into butts, or butts wanting dicks, if that weren't immediately obvious. If we do successfully insert child E into a node D, if we found a node D and we can give it child E, we continue outer. Now outer is the named while loop, so you can name loops in Rust. And so what we're saying is go to the next iteration of this while loop, which is just going through the lines in our file. If this doesn't happen, then we'll carry on down here. So in this case, we're looking for a node D. It does not exist. It's neither in the main head nor in the orphans. So we will create D. We will give it the child E that we've created, and then we will push it into orphan nodes. So far so good, except that I've been making the assumption that the first line will always start with the common center of gravity, com. And so the world is building up from around here. That's not true at all in the main input data. It's somewhere randomly in the halfway file. So what I've done instead is go, well, okay, actually, if the parent we've just created is com, set it as the head. Now, head was initially initialized as some dummy value, and it has to be initialized as something because we use it. If it's not com, put it into the orphan nodes. Great. And then thus ends the while loop. I can take this out here. This was more of a test thing. We have to have an initialized head. I could have done let mute head, right? It needs a type annotation, but this is perfectly valid Rust. This is fine. except that before this ever gets written to, or effectively before this ever gets assigned to, we are checking head here to see, can we find a child node in our head node? Now Ross doesn't know this doesn't exist. So use binding head, possibly uninitialized. The compiler errors from Rust are very, very good. Head is used here, but it's possibly uninitialized, which obviously would be invalid. This is kind of the equivalent of a null pointer dereference, being like, nope, can't have that. So the two options are either we make head an option, and I do an if let sum head sum, if let sum head is equal to head or whatever, do this. Or the cheap and easy way is just initialize a dummy head, which is never, ever, ever going to match, right? It has no children, it has no ID, no orbits will be inserted into here because, you know, this line here is going to look for a node B. Well, that's not B, it's just an empty string. And so I've completely, before I was creating my first head node off of the first line, not allowed to do that anymore. So this is going to go through all of the lines, and it will just say, okay, I'm going to put you in the orphan nodes if you don't have a parent that exists. Orphan nodes can themselves have children, that's fine. If you do have a parent that exists in the head, get pushed in as before. Otherwise, if your parent exists in the orphan nodes, you'll get pushed in there. And then the magic of the orphan nodes getting pulled out is extract if. Where have I got my extract if? Here we go. So it's going off the line. So this bit here is saying, if we had the situation where is this situation here? We're saying that node B has a child called D. Now before, we were just creating the child, saying it has no children, boom. However, D might already exist in orphan nodes, and it could have loads of children. So here it is. So B wants a D, but wants a dick. We need to check that D does not exist first. And if it doesn't exist, this is the else, we're going to create a D, a strong, hard D. If it does exist, though, well, we're going to look through the orphan nodes as a vec. It has a function called extract if. In this case, we're giving it a range to look over, i.e. the whole vector. If you find some node where the node ID is equal to the child ID we're looking for, that's D. So if you find a node called D, extract it out of our vector. That's permanent, it removes it from the vector, it's taking it. This is going to return an iterator because it could find, in this case it won't, but in general case you could find multiple items that match this pattern. We're going to call next to take the first item. So this is quite dangerous doing this because possibly this is going to give multiple matches. We're just going to delete the other two because this iterator goes out of scope as soon as this is done. We're taking next. Next returns an option. So if our iterator had found 10 nodes, we'll get a sum of the first node, and then the iterator will next again will point at the second node. In which case we can do our if let sum trick. Otherwise it will be none, and we end up in our else. So if we find D in our orphans, we give D to B. If we do not find D in our orphans, we create the child D and then give that to B. Whew. And this all means that we don't need to keep track of who our parents are. Because the instant, because every time a parent comes along looking for its child, if the child exists in the orphan nodes, it will take it. Let's call it adoption. It will adopt it. If it doesn't exist, create it on your own. No sexy times. Oof. This looks pretty disgusting. There is almost definitely a much better rusty way to doing it. This is essentially just what happens when you go, oh, I need to fix that problem. Oh, I need to fix that problem. Yes. But it works. I might very quickly just see what part 2 is. I will go and do some holiday planning. I'm just going to read part 2. Except the internet is very slow because I'm uploading day 6 part 2 now, recording day 6 part 3, trying to look at the real day 6 part 2. Honestly, it's a mess. I should not have called it parts 1 and 2. Or parts... I shouldn't have called the bits of video parts. How many orbital transfers do I need to get to Santa? Start of the object you are orbiting. Ugh. Destination is the object Santa is orbiting. Oh no. Yeah, no, we're definitely doing this in a different... No. I'm going to go plan a holiday.